think so far we've talked about a number of different kinds of models, both in a maximum likelihood and a Bayesian setting. All of those, the diversity of models we've talked about share kind of a common thing in that they're all parametric models or models that we think about as having parametric families. And so that just means that, we assume, for example, that if we're modeling process variation for a random walk, or we're thinking about observation error, we're thinking about those as being drawn from certain distributions that we can write down. And so the process error is typically normal, and the observation errors have been, they've been normal, but we've also, with some of the Bayesian models, I was including some examples with, for count data, like DLMs and things like that. So all of those data, all those models are really parametric models. And as kind of a tangent, I wanted to talk about some models that we think about as being maybe semi-parametric models and non-parametric time series models, because these models are often useful for certain kinds of problems that we might encounter. Let's see. Okay, so the three kind of flavors of things that I'm going to kind of talk about today are kind of Gaussian process models, which is something that I kind of did it in reverse. I talked about Gaussian process dynamic factor analyses a few weeks ago, where instead of modeling trends as being a random walk, we're modeling them as this smooth process and trying to infer that. So it changes our interpretation a little bit. Also introduce kind of these neural network models and how they apply to time series type problems. And then finally, we'll talk about empirical dynamic modeling, or EDM as it's known, for these kinds of problems too. Okay, so I think there's kind of a link here between some of these types of time series models and then the exponential smoothing type models that Eli was talking about for forecasting. And I think the linkage here is really that when we use these kinds of models, we're borrowing information from neighboring points. And the borrowing occurs slightly different ways, but like an exponential smoothing type forecasting model, we're going to be basically borrowing information from past data and use that to predict the future. Some folks have maybe used, well, I'm sure that everybody in class has probably used a GAM at some point in your academic career. So GAMs are just another kind of way, or another kind of flavor for how we might borrow information from neighboring data points to inform kind of the trajectory that a population might have. The key difference with like a GAM and what we've done in the class so far is that inference is no longer made about the say your process variance. So it's not we're not trying to make inference about the variability year to year. Instead, we're trying to make predictions over kind of the mean population trend, for example. And so GAMs are really useful because they're kind of a stepping stone to a few other kinds of approaches for these kinds of borrowing type problems. But first, I think it's also kind of important to understand that kind of the guts of what's going on with the GAM. And so the GAM model just can be written as a linear model where we have some intercept beta naught plus some smooth function represented by this f thing. And just like regression, we assume that the response is parametric, and so in this case, we can assume that observation or residual error is normally distributed. But really, the focus or the interesting thing about a GAM and what sets it apart from the models like the random walks and state space models we've worked with is really the smooth function. And so the smooth function takes a number of different arguments and can be specified in different ways, but it takes essentially it's going to be a piecewise function where we take kind of the domain of data that we're trying to smooth over, whether that smooth might be over time or might be over some covariate of interest. So if it was over either, essentially instead of modeling the relationship between time and our response as being a linear function, we're going to let it be some nonlinear function, which is cool if we're interested in trying to estimate thresholds or change points in data, for example. And the smooth function can take on a wide range of flexibility that we're gonna call wiggliness, and both the shape of that is going to be very, very flexible. So that smooth function, that f, is really generated by some underlying series of functions. Just to illustrate kind of a simple example of how this works, I'm just gonna kind of walk through with basis splines or B splines, which are a really common choice for using these types of smoothers. There's a function in R. There's a splines library, and the BS function is in that library. But this basically lets you pass in a vector of data, or kind of a vector of points that you want to create the splines over, and it returns this matrix B, which represents a series of those functions at defined values. And you can choose basically how, you can choose as to specify that function in as many values as you want. So if you have a time series of 100 years, for example, you could choose to specify to create that function at every year. So that would be a dimension of 100. If you had data to maybe data and really nonlinear processes, you could specify that to be much longer. So you could make that be monthly, for example. There's really no limit, or you could, or if data is patchy, you could alternatively specify the function every 20 years. So it's really flexible, but that's something we decide kind of a priori before we create this object. And so this is sort of what the results might look like. This is kind of a B spline of order 3 and of order 6 on the bottom. And what we end up doing is for each at any different point in time, we can think about our response variable as being just a linear combination of these different colored curves. So so early on in the time series, whether we're working with, say, the third order or the sixth order series of B splines, the purple curve would really dominate the signal, versus later in the time series, we'd expect that green line to potentially dominate the signal if the population was or the trend was increasing. Okay, so kind of when we overlay our data, what we feed into this type of approach is our B matrix that we get out of with that BS function. So we estimate this B matrix. We don't even estimate the B matrix. We create it, and then that's an argument. So that's data, and then our X is maybe our time covariate. So that's also data. So the only thing we actually estimate here is some intercept, the beta naught, and some vector of regression coefficients, the little b. And that just represents, again, that linear combination of weights that tells us how much each of these curves is contributing to the overall expectation of our data. So in practice, this is sort of like what our predicted mixture would look like for the case where we were fitting 6 different basis functions to the data. You can just, based on eyeball method, maybe towards the end of the time series, this captures the overall trend really well, but it certainly doesn't capture the beginning of the time series where the data are much more wiggly. So in practice, we would want to probably consider a wide range of different numbers of basis functions, and then let some kind of measure of kind of predictive performance tell us which of these is best supported for the data. So in reality, especially for a time series of 100 years, maybe using 15 or 20 functions would be better than 3 or 6. Okay, so one decision point then is how many of those curves are we going to generate a priori. A second dimension or point of consideration is really how where are we going to evaluate that function. So going back to my example, if we have this time series of 100 years, are we going to do we want to evaluate the function every year or every 10 years or every month? And so there's a wide range of options. Again, we want to decide about how, I guess the trade-off here is really that the more points we're going to be evaluating that function at, the more wiggly our line will be, and essentially it'll have more parameters. So we could potentially be overfitting our data if we make it too complex. And in contrast, if we just fit a straight line through the data, then it's going to be a very simple model like a regression with 2 parameters, and potentially could be underfitting the data. So I think we have to really think about, not just how many of those B splines we want to include here, but really, where or how many function evaluations we want to actually make. In most cases, we want the locations of essentially where those those pieces are of the function to be evenly distributed throughout the data. So just using the air miles data set, which has 23 points, these would represent our kind of 10 equally spaced locations throughout the data. But if our data was more patchy, and we missed a lot of observations, then it would be more difficult. So maybe we would still want to have the locations of these change points to be distributed throughout the function, or maybe we would want them to be spaced more closer to the actual data. And these kinds of decisions are going to affect not just the shape of the function, but also our standard error. And so in places like in the middle here, if we didn't collect a lot of data in the 1950s, for example, we're going to have our standard error, the standard errors are really going to blow up like they would with a random walk model, because the further we get from data, we're just going to be much more uncertain about the shape of that curve and what it looks like. So that's just kind of the background with the GAMs. But I think and to kind of recap what the GAM is actually doing, it's really modeling a change in the mean, and so this is going to be important when we differentiate it from the Gaussian process type model. But this smooth function is just affecting the overall mean trend, and so the smooths are very flexible. They're available in a wide range of packages. MGCV is really a really powerful tool for doing this, or BRMS in a Bayesian framework. And there's a lot of other good references out here that I've linked to that are really worth checking out and diving into. But that's essentially all I'm going to talk about with the GAMs, because I just really wanted to use the GAMs to set up kind of the contrast with the Gaussian process models. So the main difference between the GAMs and these Gaussian process models are how we're specifying this smooth function. And so with a GAM, remember, we were specifying a smooth function and really modeling a change in the mean. And with the Gaussian process model, what we're going to do is use this covariance matrix that I kind of talked about during our Gaussian process DFA example. We're going to use this covariance matrix to model the change of this function through time. And so both of these approaches are similar in that they're using the neighbors to really constrain the shapes of the functions. But the difference being that Gaussian processes use this covariance. So just to the parallel to the GAM, again, we have some smooth function that we want to estimate. This black line might be our overall mean prediction that we're trying to generate, and the red points are the observed data. And so with the Gaussian process function, we have a covariance matrix, and every element of that covariance matrix is defined by some function. We could be estimating the value of that function at each point in our time series, and so that's in this case that would be dealing with a matrix that would be 100 by 100, which sounds pretty large, but in practice, it's if every element of that function is if every element of that matrix is a function of only 1 or 2 parameters, then it's actually pretty straightforward to implement. The challenge is if we're starting to do this estimation, especially in a Bayesian framework, and calling the multivariate normal likelihood a large number of times, we're having to invert this 100 by 100 matrix, which is computationally just challenging, even if it doesn't actually involve a lot of complexity with a lot of parameters. So an alternative approach, instead of using the full Gaussian process model, sorry, the slide was cut off, is instead of using the full Gaussian process model, we'll use what's called a predictive process model. And so the GAM worked by taking our function and breaking it into these series of knots and essentially creating a piecewise polynomial between the segments. What the Gaussian process is going to do is we're going to treat essentially the locations of the blue dots on this line as being a random effect. And we're going to estimate those values, and given those estimates and the covariance matrix, we're going to interpolate the values of the function between the blue dots. So, again, we are going to parameterize the covariance matrix the same way, just in terms of the a couple of parameters. But then we're just going to be evaluating this function at a smaller number of points. And this Gaussian predictive process has the overall effect of kind of smoothing out any trends in the mean. So there's lots of applications that I'm linking to here. I'm not going to really get into them, but some really great background. I think for a lot of the applications in fisheries, I think that Steve Munch has done a lot of really great work with this. And there's also one of my favorite papers is this paper by Latimer in 2009, which in Ecology Letters, that gave a really good overview of the Gaussian predictive process approach. It's very readable. If you want to adopt these methods, it's super useful. So you can check those out on your own. All right, so we're thinking about applying these Gaussian processes to time series, and we have several options for estimating our function at these different knot locations. Everything is in the Gaussian process world is going to be determined by this covariance matrix sigma. It could be, we could also have some mean vector that we estimate, this u, but we don't actually, we don't in general estimate that. That's usually a vector of zeros. So all of the parameter inference is really based on what's going on with sigma. So as I said during the Gaussian process DFA lecture, one of the challenges here, or one of the reasons we use Gaussian processes, is that if we have this giant covariance matrix of 100 by 100, we can't estimate every parameter in that matrix. It's just not identifiable. So you could do all kinds of tricks, like zeroing out some elements that you don't care about, or create some block matrices within that. But there's a lot of challenges with those kinds of constraints, especially when we're trying to do complicated estimation. And so instead, what we do is, every element, as I said, is going to be this function that we're going to specify a priori. That can be, it's called a covariance function or a kernel. The common choices of that are things like the exponential and squared exponential, or the Matern function. All of these are widely used, and so I think it would make good choices for analyzing this kind of data. So what this looks like in practice with the exponential function, for example, is that if we have, I talked about this with the Gaussian process model, or DFA model, but sigma, each element of sigma ij is just going to be some covariance that we specify as a function of sigma squared, which controls the overall magnitude of that function, as well as some decay parameter tau. And so in this framework, d, or dij, is just going to be data. It's the distance between points I and j. And these could be space and time, or space and time. But what's great is that this simplifies the estimation approach. Instead of estimating a giant matrix, we're only going to be estimating two parameters here, just sigma and tau. So so very flexible. Some of the other different kernels that I talked about have three parameters, but still it's not overwhelming. Okay, so the question is just like for our exponential function, if we're thinking about this with time series, how does sigma and tau control our wiggliness? And so, as I said, sigma controls the magnitude of variability. And so if we think about this with time series data, the larger sigma is, the larger our variability will be between time series, or over the course of that function. And so sigma is going to make the peaks and the troughs of this function as we're fitting it through data be larger. And in contrast, tau is going to make the whole exponential term closer to 1. So that's going to really control how quickly the function decays as we get further away from the values at those knots. Okay, so I think the linkages here to our state space models that we've talked about in the class, and kind of the parametric approaches like that, are these are generally used because the focus of inference might be our process variance or observation variance, or the ratio of those two, for example. Or it might be on some of the random walk processes. But separating it out in this framework is also kind of for convenience, so we can estimate each source of variability. But there's no reason why we can't also do this in the Gaussian process framework. So, you know, basically every model in this class that we talked about so far in the parametric framework could be, we could substitute a Gaussian process in there in its place. And so this could be done with a, you know, a DLM or a DFA model or a MARSS model that has multivariate time series. I illustrated with the Gaussian process DFA a couple of weeks ago what that might look like. Our simulated trend, you know, with a AR process might be something like this. And if we wanted to fit this with a Gaussian process type approach, you know, we would have to make some choices about what the covariance function might look like and how many knots we might have and where those knots might be. So using just a really simple, I mean, the kind of on the simple side of things, we could specify a model with very few knots. And so, or these knots are essentially breaks in that function. And obviously the smaller that is, the coarser this function will be. It won't be a very good approximation of the data that we're trying to or that function that we're trying to estimate. As we increase this to 10 knots, it seems like we're doing a little bit better. And then once we get to, you know, 25 knots, we start to get something that approximates our data a little bit more. The difference, I guess I should say, even with 25 knots, that's still pretty good because we're still estimating about half as many parameters as we would thinking about our states as we would in like a state space random walk type framework, where each of our latent states is being treated as a parameter. Okay, so that's kind of the overview of the Gaussian process stuff. I'm going to you know, refer back if folks are interested in implementing that in practice. The Gaussian process DFA is a pretty easy way to do that, and all that code is ready to go. And so then I'm going to transition here to start talking about some other kinds of models, specifically going from the Gaussian process models to using what are called neural network time series models. And so neural network models have been used, you know, in environmental sciences for at least the last 20 years or so. They're starting to see more and more uses as people are using machine learning tools more frequently. This is just a handful of kind of recent papers that I think have used them. But there are special extensions to these kinds of models for using data that are structured either in space or time, and these models are very flexible and can handle that kind of structure. I think the other advantage of using these neural network models is that with the Gaussian process type model, we were using it's often referred to as kind of a semi-parametric approach, where we're assuming that there's a parametric model that controls our observation error, but the wiggly function that we're trying to estimate is kind of non-parametric. And so in the neural network time series type framework, it's different in that we're going to take a step away from the parametric field of models and go straight into something that doesn't have an underlying statistical model. So this is going to be more of a machine learning approach. Some people think about these as black boxes, but I think it's much more easier to understand than sometimes what it's made out to be. I think the most, in my opinion, I think that these models are very very tractable and useful. I think the most intimidating part of them is probably the language and the jargon that's associated with kind of working through the literature and learning what folks are actually doing. But I think if you can work with, say, logistic regression, you can do neural network models. It's not actually that difficult. So the language that we're going to be using here to talk about neural network models are going to be inputs or input data or an input layer. And so the inputs are just going to be our predictors. Then we think about the next level is going to be the hidden layer. And so the hidden layer is like in a state space model, we think about these are unobserved processes or latent variables. And so the neurons are going to be controlling the dimension of the layer, and so the layer is going to control the layer size. And then finally, the output layer is going to be the predictions that we make against our actual data. These predictions, though, are going to be non-parametric. So I think one of the challenges here in these kinds of models is we're not going to be generating a prediction with an accompanying standard error. We're just going to be generating a prediction. And if we want to estimate standard error or some measure of uncertainty, we're going to have to do that a large number of times or validate it in other ways. Okay, so this is a little bit different approach from what we've used. I think, as I've said, that they're very powerful because they're also nonlinear functions, and so we're not going to be constrained by any functions the way that we are in MARSS or with a DFA. We have any number of predictors that we could use for our time series, and so with with data that's structured in time, often what people use is they'll take a time series and use past observations, obviously, to predict the future. So we just have to decide how far back in time we want to go to make those predictions. Okay, so our neural network is going to take our input data. We're going to specify how far back to go in time, and then we're going to use a series of functions to generate our predictions. And this function is often in the neural network literature will be called the activation function. It's just some nonlinear function that most often is either a logistic or sigmoid function. So this is where the connection to logistic regression comes in. We're just basically going to be doing a series of logistic regressions over the course of these our data and our kind of hidden states. So this is what the neural network might look like. This is a very simple example, but I wanted to just kind of talk through the different pieces. So in this case, our data are going to be, we're going to say that we're going to be using, so this is a time series. It's going to be very simple with only 4 data points. We're going to be using data points 1, 2, and 3 to predict our 4th data point. And so our input layer here is going to be our x's, which are just x1, x2, x3 on the left. And on the right side is going to be our output layer. So that's going to be our prediction of what the time series will be at time step 4, for example. So that's just this g of x function. So all of the action here really happens with what's going on in the hidden layer. And so the hidden layer here is represented by the middle set of circles or nodes, and these are denoted with A. The superscript on the A's just represents kind of the second layer of the network. And so in this case, our primary layer, the first layer is the input layer, the data. The A's are the hidden layer, the second layer. And then if we wanted to put a superscript on the output layer, that would be 3, obviously. So our decisions here are both how many hidden layers are we going to have. And so in this case, we have just one hidden layer. And we say with our in the neural network language, we have 3 neurons here. We could have a second hidden layer, and that could also have another 3 neurons. And you could potentially add, any number of layers that you wanted to this problem, and each of those layers could be dimensioned by any number of neurons. And so in general, in practice, people often parameterize these the number of neurons in any layer to be the same size or smaller than the size of your input layer. And so in this case, we have 3 layers in our input layer. So a good rule of thumb might be to keep our hidden layer from being 3 neurons or smaller. And then for these kinds of time series type problems, I think it's really common. I mean, these models are very flexible. There's very, very little need probably to explore models with more than 2 hidden layers. One hidden layer and a small number of neurons, as we'll see from the examples that I'll talk about, is going to be a really powerful approach to generate really good predictions. So those are the kind of the language we talk about. The blue arrows here represent the estimated effects of each of those different neurons on either the layers that are basically the layers that are coming after it. So we see, for example, that X1 has 3 arrows from it going to each of the neurons in our hidden layer are A1, A2, A3. Similarly, with each layer in each of the neurons in our hidden layer, A1, A2, A3, those each feed only have one path to go into our output layer G. So each of those arrows corresponds actually to a coefficient that we're going to have to estimate. So in the case we're going to, and we can do this. I'm going to use different symbols to denote this, but we're going to estimate essentially a matrix of a 3x3 matrix of coefficients that describes kind of the jumble of arrows on the left relating the relationships between the input layer X and the hidden layer A. So that's going to be a matrix of 9 coefficients, 3x3. Then we also have to estimate a matrix or a vector of three coefficients describing the effects of the activation layer, or I'm sorry, the hidden layer A on our output function, the G. Okay. So as I was saying, I think that the language can be intimidating here, but essentially all we're doing here is we're going to be doing logistic regression, where we're estimating this matrix of coefficients, and then we're evaluating the logistic function as a function of those. Okay, I talked about this. We have to estimate the different layers of coefficients between each of the different levels. This is what this looks like mathematically. So for example, if we just wanted to look at the coefficients between our input layer and our hidden layer, we're estimating this 3x3 matrix, which I'm going to call theta, and this just relates each of those input layer values x1, x2, x3 to the latent or hidden layer or value of A1, so the neuron A1. The F function here is usually the logistic or sigmoid function, but this can be any number of other functions. But this is as simple as it gets. So this is how we do the first part. The second part is going to be to relate the values of those hidden layers. So the neurons in A1, A2, A3 are related to our output layer via this, again, some logistic or sigmoid function. So so we do estimation. In this case, we're going to be estimating, essentially 9 parameters for controlling the input to the hidden layer, and another 3 controlling from the hidden layer to our output function. As I said, we can vary. This can be very complex or very simple. I would say if you're going to apply this in practice, let's try to keep it pretty simple, because we can fit very powerful models that have good predictive ability with only a few neurons in our hidden layer and with only one hidden layer. So I'm not going to be talking through examples in this class that have more than one hidden layer, for example. It just gets overwhelming, and honestly, the predictive value of those extra layers is just usually not worth it. Okay, so there's a couple packages in R that make this very user-friendly and easy to work through. We've walked through the forecast package before and used it for this class, and that's going to be primarily what I'll talk about here. So the forecast package has a function to basically implement neural network time series models. It's called NNETAR, and so this will implement neural network models with what's called autoregression. And so I talked about how if we're going to make a prediction about a given value, we're going to be using the data in the past to predict the future. So we're just going to have to specify our lag of how far back in time we want to go to make these kinds of predictions. There's a really great tutorial and vignette I've linked to here. So if you're interested in these types of approaches, check it out. So as an application, I wanted to find a data set that was fairly noisy and maybe difficult to predict. And so this is just a daily stream flow from data on the Cedar River. It's just a USGS water gauge. And this is just kind of the time series over the course of a year. We can see in some portions of the time series, things might be really predictable, like maybe in end of summer here where flows are low. But there's also times where flow is quite variable, especially when winter storms might be high, and we see these flow being much more dynamic. Okay, so to use this function, there are a couple important arguments. There's only two really, I think, that we'll talk about here. This first is this variable p, which controls what's called the embedding dimension, or essentially how many lags we want to use to predict our time points in the future. So an embedding dimension of, like in the neural network example that I put together with the schematic, if we had 4 time series and we were using the past 3 values to predict the 4th, then our embedding dimension would be 3. Okay, so that's the embedding dimension. The size represents the dimension of that hidden layer, and so the size in my example that had 3 neurons, and so the size of that hidden layer would just be 3. So we're only going to be considering here cases where we only have 1 hidden layer, and that's going to have any variable number of neurons. Okay. So just to illustrate, I mean, this is kind of how we would do a sensitivity to look at, how much or what effect does varying the number of the embedding dimension. So if we vary the lag that we're going to be using to predict our future data, how much does this matter? And so this would be one way to look at that, and this would be using embedding dimensions of 1, 5, and 15 time steps. So the embedding dimension of 1 just uses the previous time step to predict the future, versus the embedding dimension of 15 would use all of the data points, all the last 15 data points to predict 1 time step ahead. Okay, so these are the predictions from the first model that just has, it has a single neuron in a single hidden layer. And I think the cool thing about this is that overall the predictions look really quite good. There's certainly times, like I was saying, where the water flow is very variable, especially in the winter, where things are maybe a little bit off, but the overall correlation between observations and predictions are 0.99, so very good. I'm going to layer on top of this the predictions that we get out of the other 2 models in red and purple from the cases where we have 5 and 15 embedding dimensions of 5 and 15 points, and we see really no change. And I intentionally didn't put a label on this because the predictions are essentially equivalent, whether we're using a lag of 1 or a lag of 5 or 15. So it doesn't really matter in this case. So next, I wanted to do kind of another sensitivity. We're going to keep our embedding dimension at 1 now, because that seemed to be pretty good fit to the data. And now we're just going to vary the size of that hidden layer. And so we're going to take that hidden layer that had 3 neurons on my little schematic, and we're gonna compare what happens if we just use a network with 1 neuron versus 5 versus 15 in that hidden layer. So just essentially a giant column of them. And again, this is the fit that we saw before. Everything looks really good if we just use that single neuron. And then again, I found there's very slight differences again in the winter. And then in the fall with using the networks or the hidden layers that have 5 or 15 neurons, the correlation between them all is also very high. And so I think in general the prediction with a single layer, single neuron seems to be really good, and for this application fits the data almost perfectly. So I think we can. So that was kind of the brute force way to do the comparison. And in practice, you would want to do some kind of model validation or some predictive accuracy to compare between those different approaches. And there's lots of different ways to do that, and many of the packages in R will kind of do that for us. But the netar function will also kind of automate that process, and so it will let us basically pass in a vector of data without specifying our embedding dimension or the size of our hidden layer, and it will tell us kind of what the optimal values are. So in this case, we pass that in, we get an object out that is kind of this form where P again represents the size of the embedding dimension and K represents the number of nodes. So in my kind of sensitivity, I looked at neural networks that had lags or embedding dimensions of 1, 5, and 15. But one of the values I obviously didn't look at was a lag of 4, and it says that the value of using a lag of 4 actually leads to better predictions. And then instead of just having a single neuron in that hidden layer, having a single layer or having 2 neurons in that hidden layer led to the best overall predictions. So the overall, thinking about my schematic that had an input layer of 3, a hidden layer of 3, and an output layer of 1 neuron. In this case, the optimal configuration it can find is kind of 4 values in the input layer, 2 neurons in the hidden layer, and then the output. So so overall, this is a useful approach for kind of doing some automated model selection. But these approaches are in several different R packages. Okay, so we've also used the forecast package in R to generate forecasts, and we can do that with neural networks kind of automatically. The overall way it does this is kind of using 1 step ahead forecast, but you could, if you were doing some kind of analysis where you wanted to create week ahead or month ahead forecasts, you could do that by training these on say 30-day time steps. And as I said, I think the difference between this kind of approach and then the parametric models that we've been using have been we don't get out these measures of uncertainty or standard errors. And so one of the ways that we can do that is by iterating a large number of times, generating parameter values from lots of different starting points, and then averaging forecasts essentially across a large number of iterations. So that's kind of what the forecast package does. I'm not going to get into examples, but there's this other package out there in the TS-DYN package, and the overall syntax is very similar. The arguments are very similar in that we just basically have to specify the embedding dimension and the size. And if you know the difference between what these things are and what these actually mean, thinking about the little cartoon I put together, you should be good to go to be able to fit these models yourself. So, so overall, I think that these are very, very approachable and useful for fitting pretty complex dynamics. All right. So the last kind of time series approach that I'm going to be talking about, sticking with the non-parametric type models, are kind of a family of models that are known as empirical dynamic models. These are widely used and have been kind of popularized by George Tsujihara's lab at Scripps. And so there's a few different flavors of these. There's kind of the initial model based on the 1990 paper is called Simplex. There's a extension of that that's a little bit more flexible that we'll talk about called SMAP. And then there's some applications to multiple time series data to kind of infer causation, and that's called convergent cross-mapping. There's a lot of really good vignettes out there. I think that, again, the language and the terms associated with these models are often the biggest stumbling block, but I think once you kind of get a handle of what's going on, it's actually not too complicated. So all of these, I'd recommend all of these vignettes and papers. I forgot to link to Peter Kuriyama's paper, but I'll do that. But Peter just presented at the quantitative seminar a couple weeks ago, and he has an application of EDM to some juvenile fish data off of San Diego. So these are all useful references. And like some of the other approaches that we've been talking about, so the EDM approach for time series is going to be borrowing information from neighbors. And the idea is basically that if we have some system that generates a time series, there's going to be some level of what looks like noise or chaos in that time series, but there's some predictability there because we've observed the time series over hopefully a long enough period, and we've potentially observed similar dynamics in the past that could be used to predict the future. So like neural networks, there's also this thing that's called a lag or embedding dimension, and so this represents kind of the how far back in the future we're going to go to predict, or how far back in the past we're going to go to predict the future. And then we also need to specify, in addition to the embedding dimension, the number of neighbors that we're going to be using to predict. This is something you don't have to really do with Simplex, but kind of defaults to the embedding dimension +1. Okay, so when we use EDM for time series, the first thing we think about is this embedding dimension. And so given what we just learned about with the neural networks, the embedding dimension here is the same, where if we have some kind of time series here, we want to predict the value where my cursor is, time point, say 101. And with an embedding dimension of 5, it means we're going to basically just walk back the last 5 points, and those 5 blue values are going to be used to make a prediction one time step in the future. Okay, so the size of that embedding dimension is obviously going to be dependent upon your system and how predictable you think the future is. So more recent values will certainly carry more weight. Maybe you don't think it's these are years. Maybe you want to restrict your analysis to just consider embedding dimensions over the last 10 years. But again, it's going to depend on your system and species, et cetera. Okay, so that's the embedding dimension of 5. We could shorten that or make that longer. It doesn't really matter, but I think we're gonna, because we have to choose that value a priori, we're gonna have to do some kind of comparison between our different models to evaluate the predictability of models that have, say, an embedding dimension of 3 versus an embedding dimension of 5 or 10. So as I was saying, the embedding dimension is going to be something that you're going to have to specify. Again, we're going to probably start with small values and then work up from there with the kind of our prior expectation is that the more recent values will dominate and be more useful for making predictions than values from a long time ago. Okay, so what this approach does is if the time point of interest is really this 101st time point, what the Simplex method does is takes the behavior at these blue dots that are the most recent time period, and then it searches through the entire time series that we've observed to find periods that have been most similar in their dynamics to these last few variables. And then from each of these different sets of variables, each of these different sets of points, which are kind of the blue circles, we can make a prediction because we have the values of the time series after those points were collected. We make a prediction from each of these sets of blue points, and then basically average them to get kind of an average forecast of what the next value will be for the blue dots there. Okay, so that is kind of the high level overview, and I think there's a lot more details in some of the material that are both on George's website. He's got it on GitHub now, and I should update this link. The REDM package is what we use to actually implement all of these methods. They have a really good vignette and really good vignette and user guide, and so I think I would highly recommend checking that out. Hao Yi has been really instrumental in putting that together and teaching classes with it, so it's also very approachable. Okay, so let's talk about some examples, because again, like neural networks, this is really powerful and really cool. So this is just using the classic links data set from the from CRAN. So there's a time series of links over time, and it kind of goes through these cyclical dynamics. So to apply simplex to this data set, the things that we have to specify are basically passing in our data, which is the first argument. And then the second argument is going to be passing in our embedding dimension. And so the embedding dimension here is going to be a vector. It means just we're going to search over using anywhere from 1 to 10 time points in the past to predict the future. And then for each of those, simplex is going to go back throughout the time series of links and find the dynamics for each of those embedding dimension values that are most similar to what we've observed currently, and use those to predict the future. Okay. So what we get out of that kind of function call is essentially a data frame that contains our on one for every row of that is going to be the embedding dimension, and then another attribute of that data frame is essentially the correlation between our observed and predicted values. So as we march back in time and use different embedding dimensions, how useful are those embedding dimensions at making future predictions? So the way to read this plot, it would be with an embedding dimension of 1, if you just use your previous links abundance to predict the future, your correlation, the predictability between your observed and predicted values is going to be 0.65. So that, overall, that's actually pretty good probably. But if we change our embedding dimension to be 2, and now use not just our last observation, but our last 2 observations, then our predictability, our correlation between observed and predicted values jumps to over 0.8. So that's strong evidence for using a higher order embedding dimension for improving predictability of these types of models. We see beyond an embedding dimension of 2, we don't see much of a change. Things might increase a little bit, and maybe you could argue for using an embedding dimension of 5, which might increase our correlation to 0.84-ish. And after that, it doesn't really do much. So if this difference is meaningful and important to you, then by all means use an embedding dimension of 5. But otherwise, I think the embedding dimension of 2 is a significant improvement over 1. So corresponding with that change in predictability, I talked about kind of the relationship between leave one out cross validation and root mean squared error a couple weeks ago. Similarly, we see as we shift from using an embedding dimension of 1 to 2, a change in our root mean squared error. So all of a sudden, we have much lower RMSE values corresponding to greater predictability with that higher second order lag. Okay, so in addition to those types of summaries, we can also get out our the predicted values of the future forecasts for these types of models. The stats only argument will basically do that for us, and we can pull out those predictions and see that overall the model does a really good job, it seems like, of using the second order lag to make those predictions in the future. There's certainly cases here, some of these peaks where the model's not doing great and not capturing the outliers, but for the most part, it does a pretty good job. Okay, so there's a bunch of other arguments that you can play with here. We can change basically our forecasting period, and you can use these arguments, the library argument and the predicted argument, to just basically move the window over how much of the time series you're using for your training data set and how much of it you're using to actually make predictions on. So if you wanted to make predictions on the last 14 observations instead of just the last observation, you could slide these around. So it's very flexible, and it's worth playing with if you're going to use these kinds of models. Second example, going back to the Cedar River data set. So this is the flow. I wanted to apply the same kind of approach using simplex now to look at whether there's any support for using higher order embedding dimensions. And so again, we're just going to use the same basic function call and only consider embedding dimensions 1 to 10 time steps in the past. Again, this is daily flow data, so it's essentially corresponding to the flow 1 to 10 days before. And this is what this is what our plot looks like. I need to fix this too, but embedding dimension on the x-axis and the correlation between observed and predicted on the y. The difference here between the flow data set and the links data set is that it seems to be much more predictable. The values of rho here are the lowest is 0.976, versus with the links that was like 0.67. So overall things are much more predictable. The second thing is that there seems to be much more of a peak in our predictability. So with an embedding dimension of 3, we get the highest value of that correlation between observed and predicted values, and then it really drops off after there. So I think with an embedding dimension of 3, we could make some really excellent forecasts using this type of approach. Okay, so I think the other interesting thing here, now that we've fit with the Cedar River data set, we fit the neural network model, and then I fit the Simplex model, and I wanted to look at essentially which of those kind of yields a higher prediction. In this case, the forecast skill with Simplex was about 0.9817, with the neural network model 0.988. So it's so both of these approaches are just insanely high. This is not the kind of fit that we could get if we were using MARSS or any of the kind of univariate AR time series models that we've worked with. So these are all overall really good. Again, non-parametric. And as I said, there's kind of these other flavors of Simplex. I think I wanted to just give a quick overview of SMAP and not talk about cross mapping, but kind of be aware that the cross mapping's out there. The cross mapping has been used in a couple fairly high profile papers to look at kind of correlation and causation between different time series. So if you have a wide, if you have time series of different environmental drivers and maybe different species of phytoplankton, and you're looking at inferring causation, this is the kind of approach that you might want to use to be able to pull out effects of variability of say just chaotic noise versus drivers. So, but we'll just talk about in a quick example with SMAP. SMAP is similar to Simplex. A major difference is that it just estimates, it is doing some local neighbor smoothing or weighting, which introduces, it basically also includes this nonlinear parameter theta. With Simplex, when we fit Simplex, we were doing a similar nearest neighbor approach, but it was assuming all of those weights were linear. So, so the benefits of SMAP are that if you have a time series and it's influenced by, say, autocorrelated noise, you might be able to apply these methods like Simplex, and it might look to be pretty predictable when in fact it's just noise. So with SMAP, what we're going to try to do is separate out the goal of it is to kind of separate out that red noise, that correlated just process variance from some underlying process that we care about. It uses a series of what are called local linear maps, and as I said, it just adds one more this extra parameter theta. This is all described in detail in kind of the REDM package and tutorial, and so I'll let folks work through that on their own if they're interested in it. But the the function call is exactly the same as we were doing with Simplex, and so applying this to the links data, the first argument again is our links time series, and the second argument is going to be our embedding dimension. This is different from the Simplex function in that the embedding function here is not a vector, and so before we were specifying that E would be a vector from lags 1 to 10, and we're going to get back our predictions, or look at the predictability of each of those values across a range of lags. Here we have to specify the lags, and instead we're going to get out a table or data frame of of the model across the different values of theta. And so theta is this parameter that controls the nonlinearities. When theta is 0, we have a model that corresponds to simplex, and so everything's linear. As theta becomes greater than 0, there's going to be more evidence or more weight for the nonlinear functions. And so I think we're just going to look at basically comparing those types of approaches. Again, I should fix this figure. Sorry about that. And just shrink it. But so this is a plot of theta on the x-axis corresponding to kind of the degree of nonlinearity in SMAP versus the predictability, so the correlation between observed and predicted values on the y. And what we see here is that when theta values are small, predictability is 0.82. Things seem to increase and are really optimal when theta is 1, and then really drop off after that. So I think there is some degree of nonlinearity here. We would choose values probably if we wanted to try to make these one step ahead predictions. Values of theta equals 1 is probably a good choice. But again, this was only for values with an embedding dimension of 2. And so with SMAP, instead of just looking over the different lags or different values of that embedding dimension, we also have to look at different values of theta. So there's kind of a two-dimensional search. So I just wanted to repeat this exercise, taking the links data. So now that we've looked over theta, let's look over theta and the embedding dimension, that lag at the same time. And so that's sort of what this plot looks like. And so each of the different colored lines here represents the predictability for a different value of that embedding dimension. So with the embedding dimension of 1, so this is just kind of the one step ahead forecasts. Remember, that was the lowest overall when we were applying the simplex model, and overall this is not doing very well. We see that when we change that embedding dimension to 2, as we saw with simplex, that's really optimal. So that's really this purple line. And for all of these different approaches, it doesn't really matter what your value of E is here for the embedding dimension. Across all of those different values, when theta is 1, you get higher predictability. So in this case, we would say that the best kind of formulation of this SMAP type model that we could use would be using a lag of 2 and this theta equals 1, and that would correspond to correlation of observed and predicted that's about 0.85. So overall, really good. Okay, so I think in general, just to kind of close, these types of approaches I've talked about today, the non-parametric methods like neural networks and EDM are super powerful tools. They're really useful for asking a lot of questions, especially if you have time series that are really long, especially, or you have potential nonlinear relationships in your data. These are definitely worth exploring. I think one of the discussion questions or things to think about is really how do these types of approaches deal with data that are noisy, so the data that have high degrees of observation error, or data that are gappy and just missing chunks out of it because surveys didn't happen for some reason. And I think the answer is in general, they don't perform very well, unfortunately. So I think with like the with any of the SMAP approaches or the neural networks, they're assuming that that the process is observed, that there's no missing values, because if you're trying to create this library of points to make predictions in the future, you need to have similar libraries for all of the kinds of predictions that you're making. So so I think that these are probably really useful tools, especially for the cases where you have kind of consistent data that's not missing in space or time or has weird high degrees of variability. Because I think if you're applying, if you have a really noisy time series and you're applying SMAP to it, essentially what you're trying to predict then is kind of your observation error or your noise, and so it's going to be a difficult problem. But with that, I will take any questions. You guys talking or something?
no. Oh, okay. Am I there?
Yeah.
Yeah. Yeah, I thought I'd make a few comments kind of like following up on what Eric said. So kind of my experience with these, mainly with EDM. I haven't worked much with neural networks. And actually, I have a question for Eric about that. But with EDM, so like a really cool feature of it is that it's totally non-parametric. You're just creating a library of what the values, all values of points that are, say, let's say lag1, okay, so embedding dimension of 1. So so all the points that are one step previous, and you kind of like think of like a plot. You could do like a 2D plot, and on the y-axis is the value of the points one step prior, and then on the x-axis is then what the value is at time t. So that plot is showing you the relationship between what happens at t-1 and what happens then at time t. And so with this method, all you do to make a prediction is you say, okay, what was the value at t-1? Okay, so I'll just look on the y-axis and find the value that's closest, and you'll decide how you're going to weight all the ones that are fairly near. And then you just kind of take, let's just say you use the closest one. Let's make it really simple. So you look on the y-axis, what was the point in the past that had the closest value to what I see one time step prior? Great, I found it. Let's use that as my prediction. And then you just sort of go down to the x-axis and you read off your prediction. So it's totally non-parametric. And Eric showed a nice example with the links data of an example where that approach works especially well. And that's where you have a time series that has a lot of structure in it. So structure is sort of like those cycles. That's a cycle is a really good example of a structure. But one of the cool things about these methods is that that cycle doesn't have to be regular. So those link cycles, they could be kind of shifting in time. So not like regularly every 10 years, right? So this method is not fitting a regular cycle. It's not, that's not how it's doing it. It's just saying, okay, what values were kind of similar in the past, and I'll find a past that looks kind of like, you know, where I am right now, and I'll use that as my forecast. I would imagine like, you know, the sockeye data that we were playing with, it probably work really well for that too. I think, yeah, I think Eric linked to this paper. I'll put it in here into the chat. So this is a paper that Eric and I and Jim Thorson was there too, where we compared a whole bunch of these models using a really big data set of real population data. And this highlighted kind of a problem with, or not, it's not a problem. It highlights where these methods are not as powerful. And that is where whatever you're trying to model has a really strong random walk to it, or a really strong autoregressive component. And it doesn't have strong cycles or some other type of structure, like a predator-prey relationship or competitive relationship, something that gives structure to the data. If it doesn't have that, these types of models don't necessarily do so well compared to something really simple. And I think the paper that we did gives you an example of an approach that you can use to try to understand, you know, what modeling approaches would be best for whatever your problem is, right? Because you've now been introduced to a lot of different approaches. And how do you decide which one is best? And so Eric's previous lecture, where he was talking about cross-validation, is the types of approaches that we use in this paper, and it's kind of a common approach to do that. Yeah.
This time series here is the one that I was using as the example for EDM to build these libraries that we're using for predictions. But I cheated here because I wanted to make it look pretty easy to pull out with your eye. So the different periods here that are most similar are equally spaced because I just replicated this time series and added a little bit of jitter to it. But like what Eli was saying is that these the time periods that are highlighted with the kind of the open circle blue dots don't necessarily have to be equally spaced like this. They could all be, a long time ago, or they could all be clustered differently than they are here, non-randomly. So there's that's one of the powerful ways that this tool is really useful, is that it searches over the whole library of points. The second thing I would mention is that following up on the kind of analysis or that paper that Eli was talking about, a lot of folks have been doing similar types of analyses. There's a lot of kind of large databases of different time series around the world, and thinking about questions like what we were interested in, which is how predictable are a lot of these different dynamics. And unfortunately, with a lot of the fisheries and ecology data that we have to work with, it's fairly short compared to the types of data, like the flow data that I showed you from the Cedar River had 365 points daily measurements. That's really rare if we're thinking about population abundance. And so I think it's both the EDM approach and the neural network approach are really powerful, but you need to generally have time series that are, say, larger than 30 time steps. So if you have a short time series, and especially noisy time series, they're not gonna work very well.
Yeah, I would say, like, for me, I've played around with EDM a bit, but I don't use it in my work because I basically don't ever work with time series that look like that. I'm looking at these very large multivariate time series where you've taken a shotgun to the data and it's just got missing values all over the place, and I've got all kinds of noise in it. So I'm going to be using, some kind of something closer to MARSS. It may not be the MARSS package. I may be implementing it some other way, either something like that, or like, I guess the Gaussian process models also are going to be able to handle the type of data, type of multivariate, noisy, missing values all over the place kind of data that I'd be working with. But they've done a lot of cool things with these methods. A lot of work with fisheries data, and I've seen a lot with like coffee data, the larval data. But yeah.
Another limitation, I guess, of them is that they don't, I guess, like neural networks are, you can change the type of response that you're doing fairly easily. So if you have, say, zero inflated data or count data and you want to predict presence absence, neural networks can definitely do that. The EDM approach cannot. And so I think I haven't seen applications of them using that to predict data other than something that is approximating a normal distribution.